Hello everyone, and welcome to today's chem lesson. Today we're going to talk more about electrons and their places in the atom by looking more at Bohr's model. Now, Bohr's model, like we've seen before, has the nucleus in the middle and some electron shells that go around the atom. We know from our discussion last time that there's the maximum of 2 that fit in the first shell, 8 electrons in the second, 18 in the third, and 32 in the fourth, fifth, sixth, and seventh shells. The question for today is, how did Bohr even discover that these shells existed? So let's talk a little bit about Bohr's experiment. Bohr put energy into atoms and he recorded what happened, how the energy was released from the atoms. And what he noticed was that no matter how much energy he put in, he always got the same couple of results. Right? That's like if you stood on the ground and took a baseball and threw it up in the air with 0.1% of your strength all the way up to 100% of your strength and timed how long it took to come back down. Right, so you throw it up with a little strength, you see how long it takes, a little bit more, see how long it takes to come back down, a little bit more, see how long it takes to come back down. And what he saw was when he did this experiment, he only got 4 or 5 different times. Right? It either came back in 1 second, 3 seconds, 10 seconds, or 20 seconds. No matter how hard he threw it, it came back with one of these 4 times. And he thought that was strange, right? Because it should come back at a different time for every percentage of strength you use, right? It should not just form these 4 data points, it should be a line, right, where it comes back at 1 seconds or 1.5 or 2 or 2.5 or 3 or 3.5 or 4 or 4.5. But instead of seeing that, he got these 4 times, and he said, that's weird. And he said there must be some sort of limit, there must be some sort of ceiling that they hit and then return. Right, it must hit this ceiling and then come back until I give it enough strength to hit this second part and then come back. And he transformed this idea into his shell model. Right, he put in this energy and the energy he got back was only 4 different wavelengths, and he says that's weird. There must be some sort of limit to where the electrons can go. And so, he also came up with the idea of exciting an atom. Right? He discovered the excited state and the ground state of an atom. Right? Electrons can be excited and given energy, right? Whether that means you're heating them up or electrocuting them or using friction. Right? Any type of energy that an atom absorbs can make the electron in the shells jump up to a higher shell and then fall back down. Right? It's a temporary change of electron configuration. Right? We're going to have something here, and then it's going to jump up temporarily and then fall back down. And we're going to see that in a bunch of detail in a second. So this energy is given to the atom, the electron uses it and jumps up, and then it falls back down. And that energy that it absorbed must be released. And it gets released in the form of light. This is where the different colors of fireworks come from, or if you've ever taken those packets that you throw in a campfire to change the color of the fire. Those are all light being emitted from certain atoms, from electrons jumping up into a higher shell and then falling back down. So let's analyze this. Let's take something like chlorine. No, sorry, fluorine. Fluorine has an electron configuration of 270, right? 2 in the first shell, 7 in the second, none in the third. If we were to add energy to fluorine, if we were going to electrocute fluorine or put fluorine in fire or have something collide, right, and give some friction energy to fluorine, one of these electrons would jump up to a higher shell. Right, it would absorb that energy that is given, jump up to a higher shell, but it can't stay there, right? That we know from last time that this is not correct, right? It should be 270. And so it will return back to the way it's supposed to be and give off some light energy. Right, it absorbed some energy, and then it will release that energy. So no matter how you give the energy to the atom, it will absorb that energy and one electron will jump up to a higher shell. And then when it falls back down, it will release light energy. Let me change the color of this actually. Now, the words that we use for these are excited and ground state. The regular electron configuration, the one that you get off the periodic table, is called the ground state. Which means that we start and we end in the ground state. This in the middle here with one electron out of place is the excited state. It's an electron configuration with one electron higher than it should be. We're always going to see just one electron out of place, though it is possible for any number of electrons to jump up any number of shells. But when we look at practice problems to make things a little easier on us, we're just going to see one electron higher than it's supposed to be. Right? Notice that I didn't change the number of electrons at all. I started with 9. Here I still have 9. Here I still have 9. Right? I never stopped being a fluorine. The only thing that changed was the placement of this electron, jumping up to a higher shell, and then returning back and releasing energy. Now, we use this for a ton of stuff. This is fireworks. So this is anything that influences the color of an element, right? When we talk about neon lights, the old neon lights that was using excited and ground state. When Thomson did his cathode ray tube experiment, that was excited and ground state that he was messing with. I already said fireworks, right? When you put something in the fire and it changes the color of the fire, that's excited and ground state. And even more impressive than that is the fact that each element has a unique combination of lights that it gives off. Right? Every transition is different, right? So this transition from the third down to the second gives off blue light. But if it had gone from the third to the first shell, or the fourth to the second shell, those are different colors. And so we get a fingerprint, basically, of each element based on the light that it gives off when you excite it. And that lets us do a little bit of color tracking. Right, this transition from the fourth to the second gives off this color of light. This transition from the third to the second gives off this color of light. From the fifth to the second, this color of light, etc. Right, each of these transitions gives a different color. And so, right, ignoring these bits that aren't particularly important, we know that if we see this combination of colors, we have whatever element this is. If this is fluorine, we know that this combination of colors and wavelengths is fluorine. If it's a different combination of wavelengths, it is not fluorine. And we can use this to help identify elements that are in a mixture, or elements that we think are part of a compound. And what's that going to look like? That's going to look a lot like this, but without the colors. So if I tell you that there are 4 elements, element A, B, C, and D, and then a mixture of some of those elements, we would look at the emission spectra, the lines that represent the different wavelengths of each of these things. And if I told you, here's our mixture, which 2 elements are seen in this mixture? if we look at this, and I change my font color for ease of access, we see that the lines match up for D and C. Right, if this is a mixture of two of these four elements, then we know that it's going to be D and C. Notice how some of the lines from B match up, right? This line from B and this line from B matches up with what we're given, but the third line is not present. It's an all or nothing type of identification. If even one of these lines is absent, if even one of these lines is missing, that means that this element is not in our mixture. And these lines that we'll see are going to line up with the wavelengths for those elements. Right? If I roll back just one slide, this, with its four lines, right? 1, 2, 3, 4, is exactly what we would see here for an element. This technique was used to help identify a large piece of the periodic table. Before we had the tools to really look at substances and determine if they were atoms elements or compounds, we would use emission spectra and compare every single element. And we would get this as an element we've seen on the periodic table, this as an element we've seen on the periodic table, and this as something we thought was an element on the periodic table that we were then able to say, actually, hold up, this is clearly a compound made from C and D. And it really helped fill in the big middle chunk, right? If we look at the periodic table, this big middle chunk of the periodic table was really filled in once we discovered emission spectra and were able to really record and look at them. Now, to wrap us up for today, I have one multiple choice question. Which one of these electron configurations shows an atom in the excited state? For the excited state, we're looking for an electron configuration that has one electron out of place. So one electron higher than it should be. And the only one of these choices that does that is choice 4. When we're putting electrons into the shells, we want to go fill the first, fill the second, and then put any leftover in the third. Right? We want to fill each shell before moving on to the next. So 2, 8, 2 fills the first, fills the second, puts the remainder in the third. That's ground state. It uses exactly what we expect. Same thing here. 2, 8, 1 fills the first, fills the second, puts the remainder in the third. That's also ground state. 2, 8 fills the first, fills the second. There is no remainder. That's also ground state. But here, 2, 7, 1 fills the first, partially fills the second, and puts the remainder in the third. This should be, if it was ground state, 2, 8, 0. But the fact that one electron is higher than it should be, one electron is out of place, marks this as the excited state. And with that, I'm going to transition us over to our Zoom meeting for questions, comments, concerns, and attendance. And I will see you there.